Surprise! It's me. Alright, so let's talk about some conservation of momentum. Starting off with our essential question, how do we apply conservation of momentum to interactions? Our objectives for this lesson, we need to be able to state the law of conservation of momentum in words and as an equation, apply conservation of momentum to various interactions, state when conservation of momentum does and does not apply to a situation, and that's it. Alright, so in this lesson, we are going to go further in depth to conservation of momentum. We've already talked about it. It's nothing new. This is a big review, but we go a little bit deeper. It's not that big of a deal. Should not be that difficult for you. So hopefully we can get through this without any issues. As always, make sure you're asking lots of questions, and if you're not doing practice problems, you're not understanding any of this. Another law that constrains what can happen. Conservation of momentum simply states that the total momentum of a system before an interaction is equal to the total momentum of the system after the momentum. Remember that momentum can be negative, such as when an object moves backwards or down. So it might be more appropriate to say the net momentum of a system rather than total momentum of the system. Because if you change directions, then your momentum is absolutely changing, but you're going to end up with a negative momentum, either in the beginning or in the end. When we apply conservation momentum, we choose a momentum in time called before and another momentum after. A force gives or takes away momentum. When a single object experiences a net force, the forces are not balanced, remember, then the object's momentum must change. Remember that a force needs time to give or take away momentum, because our change in momentum equals force times delta t. This is our impulse. For a system of objects, internal forces transfer momentum from one object in the system to another object in the system, while external forces transfer momentum to or from an object in the system to or from some object outside the system. So you can lose some of your momentum within your system to an object outside of the system. That's absolutely possible. But you can always track where the momentum goes. Momentum is conserved if there are no external forces acting on the objects in a system, or the external forces are balanced, or the before and after moments are a very short time apart, so that the external forces have no time to give or take away any momentum. Let's say you have a car that moves on a straight roadway with a constant speed. The driver applies the brakes so the car comes to rest. Before the brakes were applied, the car's momentum was P equals mv. After stopping, the car's momentum is P equals 0, because there is no v. Is momentum conserved? Misconception says it is. Momentum is conserved because the car's momentum turned into heat or thermal energy. Momentum and energy are totally different things. The car's kinetic energy became thermal energy in the brakes, but momentum cannot be lost to heat like energy can. Different types of energy, kinetic, potential, and thermal. One type of energy can become another form of energy, but there is only one type of momentum, P equals mv. That's it. There's no potential momentum or momentum lost to heat. So if the truck's momentum, P equals mv, becomes P equals 0, then some other object now has momentum, P equals mv, and is moving. What object is it? Any ideas? What force takes away the car's momentum? Friction from the roadway. So the roadway is the agent of the force that takes away the momentum. And the roadway gets the momentum. The roadway is attached to the earth, so that means when a car stops, it transfers its momentum to the earth, and the earth now moves differently. course, momentum is P equals mv. And if you have if you have P, which is the same for both situations, P before equals P after, in the first one, m times v. In the second one, m times v. Well, when you have a much greater m, let me write some of this down. This is good stuff here. So we have P equal to each other. So this is the truck, and then this is the Earth. M, I'd say that's a pretty small v, and a bit big of an m, equals momentum of the Earth. What's the mass of the Earth? Just absolutely enormous. So then what's the velocity? Yeah, like nothing. Because our mass is so large. Also, when a car speeds up, it takes momentum from Earth, so Earth's motion is changing. When a car makes a turn, the car's momentum changes direction, so the Earth's momentum must also change direction to keep the momentum of the car-Earth system constant. If there are two objects in a system, let's call them A and B. We relate the initial momentum of each to their final momentums with this equation. This is just the initial momentum for A plus the initial momentum for B equals the final momentum for A plus the final momentum for B. The subscripts A and B are for the objects A and B. The subscripts I and F are for initial and final. Nothing new or surprising there. Remember that an object moving down or left or backward has a negative velocity. That's going to be the thing that's going to trip you up. You're going to forget about the negative. If you're not careful about sketching out the situation, if you're given a word problem without diagrams or anything else like that, just draw a quick sketch. What exactly is happening? If it's a ball going into a tennis racket, then you know that ball has to go backwards, right? So there has to be a negative momentum. Sometimes the objects A and B will stick together as a result of the collision. In that case, we treat them as a single object after the collision, and we're going to use our initial momentum for A in the beginning. Very funny. Plus our initial momentum for B equals our final momentum. Just one momentum. Our masses have combined here because the object. Sometimes the objects A and B start as a single object and split apart at some point. In that case, we treat the objects as a single object in the beginning. So it's just this equation flipped in reverse. I call that an explosion. There's our combined masses times the initial velocity rather than the final velocity. And then the two objects separate. It becomes mass A times VAF plus mass B. If there were three objects, then you would have three momentums. However many objects there are going to be however many momentums you have to deal with. You're not going to get more than three.